Hey guys, welcome back to AlgoYogi. We are doing graph series and our next problem in the list is find eventual safe states. Let's go to LeetCode and give this problem a read. There is a directed graph of n nodes with each node labeled from 0 to n minus 1. The graph is represented by a zero indexed 2D integer array called graph, where graph at ith index is an integer array of nodes adjacent to this node, basically the neighbors of that particular node, meaning there is an edge going from node I to each node in that particular list on that index. Now a node is a terminal node if there are no outgoing edges. A node is a safe node if every possible path starting from that node leads to a terminal node, okay, or another safe node. That is also basically a safe node. Now return an array containing all the safe nodes of the graph, and the answer should be sorted in ascending order. All right, so this is the graph that's given to us. Let's understand what are being asked. Okay, so here is our graph that's given to us, and we have basically also this is the representation of this particular 2D array, which will be given to us as a graph, and here next to each index 0, 1, 2, 3, 4 and 5 and 6, this is given to us as a 2D array, and next to each node, which is represented as index are starting at 0 going to n minus 1. Really important to understand. And here we are going to have the list of neighbors. So outgoing edges are going from this particular node or index to these neighbors. So for 0, these nodes are 1 and 2. For 1, these nodes are 2 and 3. For 2, these nodes are, there's only just one outgoing edges to 5. For 3, it's 0. Then for 4, it's 5. For 5, there is nothing going outward, and then for 6 also there is nothing going outward. So 5 and 6, they do not have anything. That means they do not have any outgoing edges from them. That means these are terminal nodes. These are terminal nodes. If these are the terminal nodes, that means these have to be the safe nodes because they do not have any outgoing edges. Then how do we find these safe nodes? So what we'll do is, I'm just going to erase this. This is for our understanding how this representation basically translates to what's given to us. Now if you see, we're going to explore safe nodes. For that, I will create a dictionary that will store our safe nodes. For each node, we will have a value. Basically, we'll mark it either true or false, depending on if we find that leading to the terminal. Now we're going to start our for loop, and then we'll run our DFS on that. So let's say we start iterating on 0. We start iterating on 0. So we are visiting right now. For visit, I'll mark one green line. That means we are visiting it. And while we are visiting that node, for temporarily, what I'm going to say is I'm going to say that it's false for now. It's basically not a safe node. So what I'll do is it's false. Let me tell you why I'm doing that. Maybe while exploring, there is a path that actually leads back to this node. That means we have detected a cycle. If we have detected a cycle, that means that all the paths from this particular node that's being visited, that will not lead to terminal. That means it has to be returned false. So if we ever were to come back to 0, as like considering that 3 has 0 as its neighbors, and during that DFS we are trying to check 0 as its neighbor, trying to visit it, we'll check that in safe dictionary, and then we'll return false. So temporarily I'm saying that this is basically false. 0 is not a safe node, so I'm mentioning it like basically false. Now let's explore all the neighbors of 0. What are the neighbors of 0? 1 is neighbor of 0, and then 2 is neighbor of 0. These are two neighbors of 0. Now because now these are neighbors of 0, so I'll start visiting one by one. So let's say I start visiting 1, and I basically will mark it as with green underline so that I can say that like I'm visiting it. Now since I'm visiting this, as I said, I will mark this false. I will mark this false. Then what are the neighbors of 1? These are the neighbors of 1. 2 and 3, these are the neighbors of 1. Then I'm going to start visiting, since it's DFS, I'm going to start visiting 1's neighbor. What is 1's first neighbor? It's 2. So let's visit 2. I'm going to mark it with, you know, 1 green line, and then I'm going to say 2 is false, right? Then what I'll do, I'm going to visit all the neighbors of 2. 2 has only one neighbor. 2 has only one neighbor. So what I'll do, I'll go to that neighbor and I'll visit it. I'll visit that neighbor, and then I'll check. I'll say that now I'm going to start visiting 2's neighbor, which is 5. So I'm going to start visiting 5. I'll mark 5 as false. But then I see 5 does not have any neighbors, right? So that means it's a terminal node, and it's a terminal node. That means I will return, and then I will basically change the value of 5 being false to 5 being true. 5 being true because it's a terminal node. That means it's a safe node. It does not have any outgoing edges, so it's gonna be true. Then I am done visiting. I'm done visiting. With visiting, I will just say, I'll mark it, you know, right, and then I come back to 2 does not have any more neighbors to visit. Then what I'll do is I'll mark it, it's done, it's done being visited, and then I will change this, because what I was trying to do is I was trying to find if any of the neighbors are false, but it has only one neighbor, which is 5, and that has the value true. Then I will mark this true. All right, I'll mark this true. Then I'm done visiting 2. What was I visiting? I was visiting 1 while exploring. When I was visiting 2, I'll come back to its parent. Now what are the second node that we need to visit for 1? Second neighbor is 3. Let's start visiting 3. What are the neighbors of 3? Neighbor of 3 is 1. Neighbor of 3 is 1, and then we will check if it's in safe. It does exist in safe, and it is false. That means we will return back basically false to it. This is now 3 will return false, and this is also is done being visited. So what I'll do is I'll come back to 1, and then I'll say that one of your neighbor leads to basically a cycle, or it does not lead to terminal. So one of the path does not lead to terminal. So what I'll say, I will basically come back to 1, and 1 will remain false. 1 will remain false, and then I will mark this visited. Come back to 0. 0 is visited. Now what I'll do is I'm going to start exploring the second node, which is 1. 1 is already, you know, visited. So we'll try to access it, but we'll see it in the safe. So that means it's visited, and it's not a safe node. 2 visited, 3 visited, and then we're going to start exploring 4. Now let's visit 4. It's being visited. What is 4's neighbor is 5. 5 is in our safe dictionary, and it has the value true, so it will return true. That means 4, we're gonna also mark 4 as, initially we must have marked it false, remember, but then we'll mark it true now. Then 5 is already visited. 6, well, it's a terminal node, doesn't have anything, so we'll mark it true. All right, so, and remember, all these values that are true, we can return them as our result. Okay, we can return them as a result. Result is an array which is going to be 2, 5, 4, and 6. This is our answer. By the way, we should have it as 4 and 5. So I'll create a result set, and while visiting these, I will basically add them to my result set if they are being returned as terminal nodes or safe nodes. All right, so let's write its code. It's going to be quite simple, and the time complexity here would be big of v plus e, which is total vertices plus edges, because that's how we are visiting. DFS has the time, most of the time DFS has the time complexity of v plus e, and space complexity is also going to be v plus e. All right, let's go and implement our solution. All right, let me make it a little wider. Then, so as I said, we're going to have a result set that is going to be empty in the beginning. Then we'll have safe I'm gonna call it safe dictionary, initially empty. Then what I'll do is I'll start my for loop for I in range. For I in range, we can say length graph, right? Length graph. And you know what? We can actually call it node. Let's call it node. And if we're gonna call DFS on this node, if DFS, that means if DFS returns true, that means it's a safe. That means it's a safe node, which means we can actually add it to my result. We can add that node to my result, and we're doing it in the order, so going from 0 to n-1. So our answer will be basically in that ascending order, which was asked in the problem. You don't trust me? Okay, let me show you. Like, it was asked right here. Okay, it has to be in ascending order. We took care of it without even thinking. All right, now what do we do now? We're gonna write our, let's return our result, and then we're gonna write our inner DFS function. So DFS, which is taking a node. Let's not write a node. Let's call it. I think we can write it a node. Yeah. For node, if this node is in safe, if node in safe, we can return the answer. Return safe and node. If this key already exists, let's return it. Then what I want to do right here is I want to basically have this value already marked false, and so that because node is being visited, and while visiting this node's neighbors, I again come back to visit node. That means there is a cycle. That means all the paths from these cannot lead back to terminal. All right, unless this is a terminal, which will always be marked, true. So neighbors, for neighbor of, we're gonna have for neighbor in graph at node index. All right, and this is what I was saying. So safe at I is going to be, not I, node is going to be false. So we are mentioning it false in the temporarily. All right, then for all the neighbors, I'll be exploring, checking, I'll be visiting it to check if all the neighbors of this node lead to terminal or they don't have cycle. So if DFS of neighbor, or I can just say it is false, then I will return safe node. I can say this, which is false, or I can just say false here as well, but this is also good. Otherwise, we are done. We are done visiting all the neighbors, and then we basically did not get stuck in a loop. That means we ended up at all the terminal node. So what I'm trying to say is, let's say we were visiting 0. From 0 we went to 1 to 2. Then we started exploring 2. 2 lead to 5. Now 5 doesn't have any neighbors. That means this whole thing does not exist at all. That means here 5 was basically, we must have mentioned 5 when it was being visited during, right, like as neighbors of 2. Then we went up, and then we already basically we declared it false, but it's not false because now 5 does not have any neighbors. So what we're going to do here is we'll change this value to true. Okay, we're changing this value to true. Okay, I'm gonna again zoom in. So we're changing this value to true, and then we are returning basically the safe node. Okay, so that is it. I think that is it. All right, now let's try to run this on examples. All right, this passes the test examples, and we're gonna submit this. All right, okay, so time complexity. Time complexity, we already talked about it. Complexity, well, worst case we are visiting all the nodes, and during all the nodes we are basically going over all the neighbors. That means we are also visiting all the, also processing all the edges. So you can say big of v plus e, which means vertices and edges, so nodes and edges. And then space complexity, since we have this safe, that means it can store, I guess, all the nodes. So that means we can say it all the v. So space complexity will be all the vertices. Space complexity is going to be big of v. And that is it. We can go back to AlgoYogi, mark this problem solved, and see you guys later in next problem. Bye bye.